Sure, here it is verbatim. The 2025 Nobel Prize in Physics, bringing quantum behavior into engineerable electrical circuits. What the Nobel Committee recognized. On October 7th, 2025, the Royal Swedish Academy of Sciences awarded the 2025 Nobel Prize in Physics jointly to John Clark, Michel H. Deverett, and John M. Martinis for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. The core achievement was not inventing quantum mechanics, but demonstrating through carefully designed experiments in 1984 to 1985 that two hallmark quantum effects usually associated with atoms can be observed, measured, and controlled in an electrical circuit on a chip that is large enough to be engineered. The Nobel materials emphasize a system big enough to be held in the hand. That matters because quantum effects typically disappear in large objects due to unavoidable interactions with the environment, heat, stray radiation, vibrations, etc. The laureates showed that if you build the right kind of circuit and isolate it well enough, a circuit containing enormous numbers of electrons can still behave as one quantum system, and you can use that behavior as a technology platform. What they actually observed. The Nobel Committee highlighted two concrete observations in a superconducting electrical circuit that contained a Josephson junction, a special weak link between two superconductors. Quantum tunneling in a circuit, in their setup, the circuit could sit in a stable-looking no-voltage condition. Classically, if the circuit does not have enough energy to leave that state, it should stay there. Instead, the laureates saw that the circuit could suddenly switch out of the zero-voltage state even when it shouldn't be able to, and the switch showed up as an observable voltage appearing. This is the circuit-level analog of a particle passing through a wall via tunneling. Energy comes in steps, quantization. They also showed that the same circuit could only absorb emit energy in specific discrete amounts rather than any arbitrary amount. Again, a classic quantum signature. In plain terms, when they tickled the circuit with microwaves, only certain microwave settings worked, revealing that the circuit had distinct allowed energy states. A key point emphasized in the Nobel popular description is scale. The chip holding the circuit was about a centimeter in size, and the quantum system involved billions of Cooper pairs, paired electrons in a superconductor, acting together. That is vastly removed from the usual one atom at a time picture. How they did it? A simple experiment made extremely quiet thumbnail. At a high level, their experiment can be explained in three ingredients: superconductivity, a Josephson junction, and extreme isolation from noise. First, they cooled the circuit to temperatures extremely close to absolute zero so that electrical current could flow without resistance and electrons would pair up into Cooper pairs. Cooper pairs can move in a highly coordinated way, enabling the circuit to behave like one collective system rather than a messy crowd of independent particles. Second, they used a Josephson junction, two superconductors separated by a very thin non-conducting layer, to create a circuit whose behavior is both quantum capable and controllable. Third, and crucially, they had to prove they were seeing true quantum effects rather than mundane, hidden heating or stray radiation. The Nobel scientific background explains that earlier groups could see low temperature saturation effects that might have been quantum tunneling, but could also be explained by unwanted external noise, for example, stray microwaves. The Berkeley team's breakthrough was to design the experiment so well that such alternative explanations could be eliminated, and then to show agreement with theory using independently measured circuit environment parameters rather than tuning knobs. The Nobel scientific background and ceremony speech both emphasize how seriously they treated isolation. They developed and used unusually strong microwave filtering. The scientific background describes a carefully designed filter chain using newly developed copper powder microwave filters. The ceremony speech conveys the same idea with a dramatic noise suppression analogy. Here is a conceptual, not to scale diagram of the kind of circuit idea involved. You can see the image in our conversation history. What was measured in plain terms, they applied a gentle push, a bias current, watched the circuit remain in no voltage, and then recorded when, how often it would jump to a voltage state. Because quantum tunneling is inherently probabilistic, they repeated the measurement many times and analyzed it statistically, much like measuring radioactive half-lives. They then fed in microwaves of different frequencies and observed that only certain frequencies changed the switching behavior in the way you'd expect if the circuit had discrete energy levels, a direct sign of energy quantization in a macroscopic circuit. Why a Josephson junction is special. A Josephson junction is important here because it lets a superconducting circuit have a quantum personality that is both strong and engineerable. In ordinary electronics, components like resistors and capacitors are excellent for classical engineering, but tend to destroy fragile quantum behavior through dissipation and noise. A Josephson junction, by contrast, is a superconducting element in which current can flow with essentially no energy loss, while still producing the kind of non-trivial dynamics needed for quantum effects to show up and be controlled. The Nobel sources repeatedly stress the conceptual leap. The circuit did not merely contain quantum parts. The circuit as a whole behaved like a quantum system, as if it were a single particle spread throughout the circuit. A useful mental picture, the Nobel scientific background uses a more formal version, is that the circuit can behave as if it sits in a valley separated by a hill from another state. Classically, it would be stuck unless pushed over the hill. Quantum mechanically, it can sometimes leak through and appear on the other side. You can see the image in our conversation history. This is also why Nobel materials describe Josephson junction circuits as enabling artificial atoms. Instead of relying on nature's atoms, engineers can build circuits whose quantum states are designed, wired up, and connected into larger systems. The Nobel scientific background explicitly notes that after these experiments, superconducting circuits became a foundation for macroscopic quantum physics, where the Josephson junction plays the role of an engineered artificial atom. How this enabled quantum computers and quantum sensors. The prize is fundamentally about discovery, but the Nobel Committee explicitly frames it as a gateway to the next generation of quantum technology, including quantum computers and quantum sensors. Quantum computers. A quantum computer needs physical systems that can act like controllable quantum bits, qubits, systems with two well-defined quantum states that can be prepared, manipulated, and measured while staying isolated enough to avoid losing their quantum character. The Nobel scientific background describes how, after Shor's 1994 algorithm intensified interest in quantum computing, researchers sought controllable qubits, and that, because of the Berkeley Group's work, superconducting circuits were clearly established as a viable platform. It then outlines the subsequent development of superconducting qubit approaches and key architectural ideas, including coupling qubits to microwave resonators, often called circuit QED in the literature, to improve stability and measurement, and it notes that the transmon design is used in multiple global efforts toward large-scale quantum computing. The Nobel Popular Information ties the historical arc directly back to the laureates. Martinis later built qubit demonstrations that relied on the same kind of energy quantization they had established, using two quantized levels as 0 and 1. Separately, Reuters reports and Nobel materials confirm affiliations that both Martinis and Deverett have had prominent roles connected to Google's superconducting circuit quantum computing efforts, reinforcing how the foundational 1980s discovery matured into a major technology program. Quantum sensors and measurement technology. Quantum sensors aim to exploit quantum effects to measure physical quantities, magnetic fields, tiny currents, weak microwave signals, etc., with extreme sensitivity. Even before quantum computing became a mainstream ambition, superconducting electronics were already famous for measurement devices. In his Nobel interview, Deverett explains that he was drawn to Clark's lab because Clark combined fundamental superconductivity research with squids, which he describes as sensing devices with many applications. That measurement culture, building circuits that preserve delicate effects and reading them out reliably, is directly aligned with what high-performance quantum sensors require. The Nobel ceremony speech makes the broader point. By learning how to shield and control these circuits so that they behave like quantum systems and interact cleanly with microwaves, the laureates helped establish superconducting circuits as a platform both for exploring quantum physics with artificial atoms and for developing future quantum technology. Why macroscopic control is the key technological step. What made this breakthrough unusually enabling is that an engineered circuit can be fabricated repeatably using microfabrication, wired up, connected to other components, tuned by changing currents, fields, microwaves, and scaled, copied, and integrated into larger chips in a way that single atoms in a trap generally cannot be engineered at industrial scale. Nobel materials emphasize exactly this step. They demonstrated quantum behavior in a system large enough to hold and control, not only at atomic subatomic scales. From a science perspective, this also matters because it creates a powerful laboratory for studying where quantum behavior persists and where it breaks down, i.e., how isolation, temperature, and design choices affect quantum coherence in increasingly complex systems. The Nobel ceremony speech explicitly highlights that larger systems must be carefully isolated to show fragile quantum effects, and the laureate's work demonstrated how to do that in practice for a many electron circuit. Contributions of each laureate. The Nobel materials describe the prize winning work as a closely linked set of experiments carried out together at UC Berkeley in the mid 1980s, with Clark leading the group and Deverett and Martinez contributing as postdoc and doctoral student, respectively. Laureate role highlighted in Nobel materials for the mid 1980s discovery. Examples of later impact and leadership connected to the Nobel narrative. John Clark built and led a Berkeley research group specializing in superconductors and Josephson junction phenomena. The Nobel popular background frames the group's program as a match to his research direction and notes Deverett and Martinez joined his group to tackle macroscopic tunneling. Nobel interview material and Deverett's remarks emphasize Clark as a model for combining fundamental discovery with measurement technology, squid sensors. Michelle H. Deverett joined Clark's group as a postdoc and helped execute the demanding experiments requiring extreme screening from interference. Nobel sources attribute the breakthrough to the trio's ability to refine, measure the circuit's properties, and observe tunneling and quantized energies. In his Nobel interview, Deverett describes working at Google Quantum AI on superconducting circuit quantum computing, particularly quantum error correction, showing continuity from foundational circuit physics to advanced quantum engineering. John M. Martinez was a doctoral student in the Berkeley group. Nobel popular background describes how the team used repeated measurements and microwaves to reveal tunneling and quantized energy levels in the circuit. Reuters reports Martinez led Google's Quantum AI lab till 2020. His Nobel interview discusses current efforts, Colab, focused on manufacturing and system engineering to build practical quantum computers, reflecting the field's evolution from discovery to scalable technology. Her essence in one paragraph. Clark, Deverett, and Martinez showed that quantum rules are not confined to tiny particles like single electrons or atoms. With the right design and extreme isolation, an electrical circuit on a chip large enough to hold and engineer can behave as one quantum object. In the mid 1980s, they built superconducting circuits with a Josephson junction and demonstrated two unmistakable quantum signatures. The circuit could tunnel out of a stable looking no voltage state, suddenly producing a voltage, and it could absorb energy only in discrete steps. By proving that such fragile quantum behavior can survive in a man made circuit containing vast numbers of electrons, they established superconducting electronics as an engineerable platform for quantum science, laying essential groundwork for today's superconducting qubits in quantum computers and for high sensitivity quantum measurement and sensing technologies.